So now in this final video for Chapter 7, we're going to look at how to predict some products. You're going to see a lot of tables in this section 711 that will tell you how to predict substitution versus elimination. You'll have to really study those tables. They are present in your textbook. We'll look at substitution and elimination reactions with other substrates. So these will be compounds that have other leaving groups other than halide, although they will react very much the same way as the alkyl halides. And so you'll have to know just to apply those same patterns to these other reactions with these other substrates other than alkyl halides. And so then we'll look at some synthesis strategies, and I'll show you some drawings which I will use to make some videos for you later, in which I need to draw on those diagrams. It won't be good enough just to talk about them here. So let's go ahead and get started. So, predicting the products. You should know, you should have realized now from everything that I've said, that you're rarely going to get just one product. You're usually going to get a variety of products. That is normal. And so one of your major goals is going, if practically speaking, for you working in a lab, is going to be trying to figure out how to reduce the number of products. If you can cut it down, sometimes you may have 8 or 10 different products, and you'll be happy just if you can just reduce that number down to 2 or 3. You'll be very happy. On the other hand, it's possible for a substrate to give just one product. And that's especially true if you're dealing with a T-butyl halide or some T-butyl compound, or if you're dealing with a methyl compound, methyl iodide or whatever, that will reduce the number of products that you're going to get. But that's sort of rare. So to understand how to use them, you're going to need to be able to predict all of the products and to know what your limitations are and how to use this information that you're just about to see. So here are the 3 steps that are given in your textbook, although I think there are more. Determine the function of the reagent. You're also going to have to determine the other qualities of the reagent, like its steric hindrance, etc., as you've seen. Analyze the substrate and determine the expected mechanisms. Also, right in here, you can put in analyze the solvent and how it will influence the reaction. Consider the relevant regiochemical and stereochemical requirements and possibilities. So now we're just going down some general guidance here. So this is a table that's present in your textbook, and this is very helpful. This analyzes your reagents. This will provide you a way to memorize the reagents and remember them by grouping them. You may remember earlier I said that usually your strong base will be an oxygen or a nitrogen anion. But here are some strong bases. These are nitrogen bases, but they are not anions. And here, this is sodium hydride. It is neither a oxygen or nitrogen anion. But the important thing about these is that these are weak nucleophiles. These are very weak nucleophiles. These strong bases, the oxygen and nitrogen anions will be strong bases and also strong nucleophiles. They can function as nucleophiles. So if you have anything from this group, it will be an E2 reaction. Here you could get both SN2 and E2 reactions. If you have a weak base and a strong nucleophile, you'll get both SN1 and SN2. And notice the different possibilities here. You'll have to remember these that are charged are going to be more reactive than the neutral ones, of course. And then you have weak base, weak nucleophile, and these will produce such a mild reaction that you're not going to get much more than SN1 and or E1 reactions. And so this is some guidance based on the reagents. You'll want to go over these and remember these, at least remember the groups, and then remember which group each particular reagent falls into. Now you analyze the substrate. Here you have primary, secondary, or tertiary substrate, and then you look at the categories, the same categories of the same categories that you were looking at in reagents on the previous slide. Now apply those same categories here and look at these when they're applied to the substrates, primary, secondary, tertiary. And notice that with the strong base and weak nucleophile, as we said earlier, you get only the E2 reaction. Here you get SN2 and E2. And now it's separated into what type of substrate you have. Weak base and strong nucleophile, SN1 and SN2. And when you have weak base and weak nucleophile, or weak nucleophile, you don't get much more than SN1, E1 reactions. And of course, there you're going to need a stable carbocation, so it's going to be a tertiary alkyl group. So this will become very useful to you when you're using the, when you're doing your homework. Regioselectivity versus stereoselectivity. This is one large table. This is all from one large table in your textbook. You'll want to use this table as you're doing your homework. It discusses SN2. You'll observe a single product in which you have inversion of configuration. So this is really a review of everything that we've talked about. E2, you're going to have the Zaitsev product. That's the internal alkene favored over the terminal alkene, the Hoffman product, unless you have a sterically hindered base. All of this is review. You'll want to go over this table in your textbook. I'm not going to read it to you here, but you can see you also have SN1 and E1. Practice these and use this table. It'll be very helpful to you. It's review. We've discussed all of this already. Now, other substrates. So these are the sulfonates. These are the sulfonates. And so the sulfonate is they're molecules in which you have an alkyl group, or here it's a phenyl group attached to SO3. So this is a sulfonate group. These are the alkyl sulfonates. So this is going to be butyl mesylate, butyl tosylate, butyl triflate. And so these are extremely stable. They're very good leaving groups. So you have this instead of butyl bromide or butyl iodide or butyl chloride. These are good leaving groups, just like the halides are. And the reason it's such a good leaving group is that they are resonance stabilized. So when this departs with the pair of electrons, the oxygen is bearing the negative charge. That pair of electrons can move in and another pair out. And so then up here, oxygen will bear the negative charge. Or this oxygen could bear the negative charge. So you've got oxygen bearing the negative charge, and also you have resonance stabilization. This is a very stable anion. This will be a very stable anion once it departs, and so that makes it a great leaving group. And so we'll look at these. Everything that the alkyl halides could do, these compounds will be able to do. So everything that we said about alkyl halides applies to these also. So you can see how these are resonance stabilized based on pKa values. Which one of these will be the best leaving group? So this is the most acidic. It's most likely to lose its proton. Why? Because you have electron withdrawing groups here. It's going to not only have oxygen bearing the negative charge and have resonance stabilization the same as these. That's what it has in common. But what makes this one so different is that you've got these electron withdrawing fluorine substituents, 3 of them, pulling electron density away from this proton, leaving the proton bare, and so the proton can just fall off. And so that's what makes this so much more acidic. This is a particularly stable leaving group, very stable anion. And so it's not reactive, since it's a very stable anion. Now, these sulfonates are very useful for one thing, and that is whenever you are trying to react an alcohol, OH is not a very good leaving group. And so the goal is to replace this oxygen-hydrogen bond with something else. Here you have oxygen-hydrogen. Here it's been, the hydroxyl group has been replaced with, the oxygen-hydrogen has been replaced with the oxygen-sulfur. So here, you haven't broken this bond. You haven't broken the carbon-oxygen bond. The carbon-oxygen bond stayed intact. So that you have retained the S configuration. Okay, what you've replaced is the oxygen-hydrogen bond, and you've replaced it with the oxygen-sulfur bond. So what's happened here is you use this tosyl chloride. This isn't a sulfonate yet. It's going to become a sulfonate. So what happens is you have oxygen will attack at sulfur and displace chloride, and so that forms this oxygen-sulfur bond. Now you have pyridine in here. This is run in the presence of pyridine, and pyridine, the pair of electrons on nitrogen, plucks off that proton. So now you have generated the alkyl tosylate, and that is how you went from this alcohol to that alkyl tosylate. And notice that the oxygen-carbon bond here, the RO bond, stayed intact the whole time. So you retain configuration. So now, let's look at this. We can use this, we can have this as a leaving group, the same way that you had the halogen as a leaving group. So when you have a starting material as an alcohol, you can convert it to a tosylate and react it the same way that you would, that you learned at the beginning of this chapter, to react alkyl halides. So now, when you have the sodium hydroxide, hydroxide can come in and pluck off a proton from the 2 position, and then you'll form the double bond at the terminal position. It has to be at the terminal position because your leading group is at C1. And so also you will have hydroxyl coming in and doing an SN2 backside attack and replacing tosylate with OH. So that's if you have a primary tosylate. Now, so this is E2 and SN2 reaction. Here, if you have a secondary tosylate, you will have hydroxide coming in and plucking off a proton off of methyl and form this double bond, and tosylate will depart. This again is an E2 reaction. or you can have a simple SN2 reaction occurring at that secondary carbon atom. SN2 reaction at a secondary carbon atom is a little bit harder, but they still do happen. And so you still get the alkene and the alcohol product just like before. Here you have the major product is SN2. Here the major product is E2 because it's harder for this to get in and do the backside attack with this sterically hindered back part of the molecule. Alcohols can also be used in substitution as starting materials. Here, notice that we're converting the alcohol group to, this is an oxonium ion. So here you have the leaving group is water. Water will come off as a neutral molecule. So the first step is to protonate the alcohol. Now bromide will do a backside attack and displace the water. Now notice this is the second instance you have in which the, let me back up. Here, it's a second instance that you have in which the OH, the alcohol, is being converted to something else, and so that now this will be able to be a good leaving group. OH is a poor leaving group, so you're converting hydroxyl into a tosylate, a good leaving group. Now, let's go forward 2 slides. Now, this is a poor leaving group, So you're going to convert it into a better leaving group. This is a poor leaving group. You protonate it. Now it's a good leaving group. It will come off as a neutral molecule. And for alcohols, you always must convert the hydroxyl group into something else in order to react them. Now, once again, you're going to protonate the alcohol functionality, the hydroxyl group, and then since this is a tertiary alcohol, it can depart. You get the carbocation, bromide, and the carbocation collapse to give you the bromide. So this part in here is what you saw earlier. It's just a typical SN1 reaction, and you have this preceding step in which the alcohol is protonated because that's not a good leaving group. This is a good leaving group. This is required. So these three structures and those 2 steps are part of the SN1 reaction that you learned. Okay, so acidic conditions are necessary in order to get the to convert this tertiary alcohol into the alkyl halide. And this, notice, this is by the carbocation intermediate. Primary carbocations won't react this way. They have to go by the SN2 mechanism. But you know that because that's the same thing that you saw in the case of the reactions of alkyl halides. Everything that you learned about alkyl halides will be directly applicable to this. Those rules will stay the same. Alcohols will undergo E1 elimination when reacted with a strong acid. So this is protonated. Then it becomes a great leaving group. And now you have this weak base come in, deprotonate. Pair of electrons moves in to form the double bond. And this is the E1 mechanism that you've already learned. Okay? You learned this when this was an alkyl halide. It's the same thing here. You just add the alcohol, this preceding step, the alcohol being protonated, converted into a good leaving group, whereas with the alkyl halides, you start out with a good leaving group. This first step is not necessary with the alkyl halides. It is necessary here, but everything else stays the same. The pattern stays the same. Now, these synthetic strategies, you're going to have to just learn these reactions. These are all the reactions that you've seen on this sort of starburst drawing, and you will need to learn all of these. There are some patterns that you can recognize in this, and I'll get an overhead document camera and print out this figure and draw on it and explain the patterns that you can recognize in here to make this easier to remember. But it will be necessary for you to remember this. These are the reactions that you've had. We've been learning a lot of procedures and a lot of characteristics of the substrates and the reagents. Now you're going to have to be able to remember the reactions also. So it does get very complicated. Those are primary alkyl halide reactions. Now tertiary alkyl halide reactions. The primary alkyl halide and the tertiary alkyl halide reactions are going to be simple because they usually give just one type of product. And again, this is sort of a starburst reaction, except it's collapsing instead of bursting. But you'll be able to see some patterns here, and I'm going to print this off and draw on it in using the overhead document camera so that you'll be able to see the patterns, and then you'll be able to learn this and remember it from the patterns and not just memorization, because I don't think that just straight memorization is going to help you that much. And so, but you will need to know this. Retrosynthetic analysis. Now, this is very brief here at the end. This is very useful to synthetic chemists. I know that a lot of you are thinking about your grades and, taking different exams and MCAT and these things. So I'll just tell you, I could almost leave this out, except for this one arrow right here. Do you see this arrow? This is a totally different type of arrow that we haven't seen before, and it is only used in these retrosynthetic analyses. And so I want to describe it just a little bit, and what you'll need to, you will be able to just do a very superficial remembrance of this, and you may not need to study it much more than what I am telling you here. It's one of these things where if you've seen it, you'll remember it, and that's probably going to be enough. So I'm going to give you the information now. So let's say that when you see this arrow, this tells you that everything is backwards. So the product is over here, and you're wanting to work out the reactants. So here is your product, and what you have to analyze, you have to look at this and say, okay, how am I going to make that? And one of the strategies is to look at this and say, well, where is my weakest bond? Which bond can I cleave? Well, we haven't been learning how to make carbon-carbon bonds, so you're not going to select one of these bonds. It's going to be one of these bonds up here next to oxygen. So let's pick this bond, this carbon-oxygen bond. That's going to be the bond that we're going to try to form using our two molecules, our two reactants. And so you have to realize that if we've been using a lot of reactions where we had alkoxides, oxygen bearing a negative charge, and here we would have a carbon bearing a leaving group. The oxygen would come in and attack at the carbon and displace the leaving group. And so that's what this is. Here we have an ethoxide come in to do an attack on carbon bearing a leaving group. So you can look at this and say, yeah, I've seen molecules like this sodium ethoxide and this pentyl bromide. I've seen those. I know what those two reagents would do. Ethoxide is going to displace bromide, and you're going to have an SN2 reaction. And so you realize that. And so as you're thinking it, this would be the arrow that you would draw when you start out with your target molecule and you're trying to figure out how you can make it. You say, okay, here's my target molecule, and I'm going to think about this. What reagents could I put over here that I might be able to use to make that target molecule. So this is not a typical reaction arrow. This is an arrow that tells you that you're doing a retrosynthetic analysis. The product is over on the left side, and the reactants are going to be on the right-hand side. So it's reversed. You need to remember that. That's what that arrow means. That's the most important part of this last very, very short section. And so from this, you would be able to generate this synthesis. Here we have what I just had on the previous slide. And so here is your sodium methoxide and your bromide. Now you draw it like a regular reaction. Here is your pentyl bromide with your sodium methoxide and your DMSO as solvent. And indeed, it does give this product. You can expect this to be a reasonable synthesis. And here it is drawn in the forward direction of the way that you expect this reaction to occur. So I want to go back one more time and make the point one last time. This arrow is not telling you a reaction that proceeds. This is what you draw when you are predicting a way to make that target molecule. Okay, so this concludes Chapter 7. And so the final thing that you'll have for Chapter 7 will be me drawing on those starburst figures, ways to help you remember those rather large assortments of reactions.